This one, my slides is not that completely ready, but I can try my best. And this one is on the second handout today. Okay. Okay, maybe we can start with this one. So Max, probably we can start with the second one today. Okay, for this. So today the second one is the containing hole, the plate with containing hole, and the problem statement is this: assuming we have a plate that has the x dimension is very big, and the x dimension is much larger than the size of the hole. And much larger, that means at least 10 times larger, 10 times longer than 2a. That's an assumption. Such that at the free boundary, the distribution of the stress is uniform. Uniform, that means it's constant, okay? For anything like a hole here, even for our fundamental study, we study the circular hole here, and they may be the different shape, and in practice, that representing the hole in the ideal model is an example of the practical crack, okay? So this kind of problem is serving as the first step toward the fractional mechanics. In fractional mechanics, we will be able to change the shape, the geometry of the hole into the different one. Then we will come up with the different result about the distribution of the stress around the hole here. And we call the hole as a defect. So basically, around the defect, as long as making the geometry from one end to the other discontinuous, then we always expect there's a stress concentration about the defect, okay? And again, we're picking up the circular hole, circular defect, because this kind of the simple geometry can provide us the closed form solutions to describe the distribution of the stress around here, okay? And that is important, and that actually have many the implementation that implies. First one, the stress concentrations. The first one implied serve as the foundations, again, to develop the theory on the fractional mechanics, on the linearly elastic fractional mechanics, okay? And even that can be provided as the foundation for plastic, the base, the fractional mechanics, okay? So this problem basically is the key to many important things. Okay. So this is a problem statement. We consider such a loading. Here in my drawing, you should imagine this dimension is at least 10 times larger than this one. Okay. And before we proceed, I want to give you some features about the problem here. So let me do this. So this is the material model, and here we have a little hole here. And this one is under uniform tension. If you have remembered from fundamental mechanics material, and we have kind of qualitative phenomena called descent principle. In fundamental mechanics material, we only describe this principle qualitatively. In that way, we're saying is this. If let me choose a few cross section, for example, here, here, okay, and let me expose the free body diagram of the three sections. First one is this one. The second one is this. third one is this. And I'm going to draw the distribution of the stress. For this one, that is pretty much uniform. For this one, due to the defect, this is closer to the defect, so its stress basically is a little bit influenced by the existence of the defect. Around here is the most severely influenced. Okay. So this principle is saying that as long as we work on a remote site, remote, that means a place. As long as we work on the remote site away from the defect, if distant enough away from the defect, then like this section here, then we can pretty much guarantee we can ignore the influence of the defect. We simply assume the distribution of the stress is uniform. So that when we pick our working sites closer to the defect, then we must be concerned about the influence of the stress concentrations. Okay. So basically, the principle simply describe the two phenomena. Okay. At that moment, when undergrad, we only talk about this qualitatively. And with these sections, with the tools we learned from the area stress functions, that will allow us to do a little bit more quantitative analysis, and that even will allow us to get the descriptions about the distribution of the stress in terms of the geometry and the dimensions. Okay, so that is the topic of these sections here. Okay. In the following contents, even in the handouts, sometimes in the handouts I use A. Okay, I use A as a radius. In the slides here, sometimes I might swap the parameter from A to capital R. So I will change that one more consistent later on. And again, even including this one, I think in the handout I using sigma, but somewhere I use sigma x. Okay, so I will let you know whenever that is appropriate. I will specify correctly to you. Again, to this problems, we are going to use using the area stress function to help us solve this problem. The whole things will be, how about this? Today we only make introductions and the follow-up next lecture videos, and I will talk about the solution strategy. Okay, so Max, we can come in here.